So today we are going to learn branch instruction. Okay, now why these branch instructions are important and what it do, that we are going to study. So first of all, where you have heard about branch instruction first, we have started with branch instruction in our pipelining lecture. If you remember, 8086 is the first processor which provide you pipelining. What is pipelining? You can do task parallel, right? And your pipeline will get fail if you are having branch instruction. Remember? Yes. Why it gets fail? Why your pipeline will get fail if you are having a branch instruction? Because normally every program is run sequentially. Yes? Why it runs sequentially? Because of IP. Now what is IP? IP is instruction pointer. What it do? It always point to the next instruction to be fetched. Yes? Yes. IP is an instruction pointer which always point to the next instruction to be fetched, and it is always pointing to the next instruction in sequence, right? So because of IP, we always fetch our next instruction. Yes? Yes. And because of that, if we prefetch something, we put it in a queue. If this is my queue, because of IP, we'll put data in a queue. Now, if suppose you are having instruction like this, if some lines, else, some lines. Now this is nothing but branching. Branching can be done using if else, can be done using for loop, right? Now if there is something like this, if my IP is currently pointing over here, now before executing this line, my IP will be pointing over here. And suppose this line are already prefetched. Understand? These lines are already there in queue. But because this is not executed yet, when this line will get executed, at that time your processor will get to know that you need to execute it or not. Suppose at this point your processor will get to know that this condition is false. So now you need to jump over else part. Yes? So you have already prefetched this much part which is already there in your queue is useless. Understand? Yes. Yes. And your pipeline gets failed. You need to flush all this data from queue. You need to prefetch everything from here again. And your IP now pointing over here. You need to change your IP. Understand? This is what happens in normal scenario. Understand? So branching is nothing but changing the value of IP. And many times because of branching, your pipeline will get failed. Yes? Clear? Where is just this one, right? Okay. So now we'll learn branching. So there are first of all two forms of branching, unconditional and conditional. Okay. Suppose there are two forms of unconditional jumps. So we want first of all understand there are two things, jump and call. Okay. Now what is jump and what is call, that we'll discuss. So suppose this is my program. Here I am having an instruction called J and P. Down is my label. Suppose this is my new code and here I am having down, and this is my code. So what happens? This is my unconditional jump. So whenever my assembler comes on this line, it will get to know that I need to jump. Where you need to jump? On down. Down is here. So what your processor will do, what your assembler will do, when you are on line jump, your IP will be pointing on this line. Yes, because IP is always pointing to the next line to be fetched. So when this line will get executed, your IP is actually over here. Yes? Yes. Yes. But we get to know that I need to jump. This is unconditional jump, so you compulsorily need to jump over this. Yes. So what happens? This IP is now pointing over here. I need to change this IP and it will now pointing over here. So what my unconditional jump instruction do? It will change the value of my IP. Clear? Yes. 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 First thing, it is unconditional jump. So when instruction comes, you compulsorily need to jump. Yes? Yes. Once you jump, what you need to do? Your assembler will simply change the value of IP. From where it will get the value of IP? From the label that you have given. Clear? Yes? Yes. Next. Same way there is one instruction called call. Suppose down. Now this is again one way of calling or doing branching. Call is used to invoke your subroutine. What is subroutine? You are calling a function in C language or C++ language. Same thing is called subroutine in 8086. Okay? Or procedure. Yes? So if I want to make a procedure is having two things, the definition and the calling main part, right? Normally you call your function from main, function is written somewhere else, your function will execute it and you will come back. Yes? Yes. So suppose call down, this is my function, subroutine, this is my code, and at the end of this code there is a statement called RET, return. Now what is the difference between this and this? Constant, proper. Here once you jump down, you come over here. Now you no need to take care about anything about here. Now you need to simply execute this part. Your work is done. Right? Here problem is once you are this line, you need to go here, execute this line. After you get RET, you need to come back over here. There is a catch. Here you don't need to come back. Here you need to come back. Understand? Problem comes over here. When you are on call line, your IP is pointing over here. Yes? Yes. If you want to execute any line, your IP should be pointing to that line. Yes? Yes. So if I want that IP should come here, I need to change IP. If I am here, I need to change my IP. At the end of the day, then when there is a branch instruction, you need to change your IP. Yes? Yes. Now understand the problem. When my IP is pointing on this, when I get to know that I need to call a subroutine, I need to change this IP from here to. So suppose this IP is containing 1, 2, 3, 4, and this down address is suppose is equal to 5, 6, 7, 8. Okay? Suppose. So what I need to do is I need to change this IP to 1, 2, 3, 4 to 5, 6, 7, 8. IP is changed. I am coming here, executing this line. Now this part is done. Now I need to not come back over call. I need to come to the next line after the call. Yes? If I go to call again, it will continuously going and it will be infinite loop, right? I need this, but I have lost this address. My microprocessor does not know what is the value of this line. How can I come back here? How? You should come to location 1, 2, 3, 4 again. But your microprocessor lost that value because you have overwritten this IP value from 1, 2, 3, 4 to 5, 6, 7. Understand? Understand the problem? Your value in IP indicates that which line you want to execute. Yes? Yes? Now, when IP is pointing over here, we know that we want to execute this line. But at this line, we get to know that we need to jump on down. So instead of executing this line, we change the value of IP to 5, 6, 7, 8. It will come over here. Right? It executes this line, complete. But now I forget the value of this because this is not stored anywhere. Understand? Simplest solution is before jumping to down, you need to store the value of IP somewhere so that you can fetch it again and you can come back. Yes? 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 Yes. Okay. So where that value is stored? That value is stored on stack because it is last in, first out. So we'll simply push and simply pop. So before going to down, what your assembler do? Your assembler will push the value of IP because at this point of time my IP is pointing over here. So my 1, 2, 3, 4 will store on stack. Then I will push fetch the value of down, going here, executing this line. When RET instruction comes, at that point of time, I will pop the value from the stack. I will get 1, 2, 3, 4, put it again into IP, and now I want to know that I need to start with this location. Understand? Yes. Yes? Yes. This process is not required when you are having jump. It is required when you are having call. Why? Because when you are having call, you need to come back. When you are having jump, you don't need to come back, you simply need to go ahead. Understand the difference? Yes. Clear? Yes. Seriously? Yes. Done? Yes. Okay. If it is clear, okay. How this 1, 2, 3, 4 stored? This depends on our little Indian rule. Lower data, lower address, higher data, higher address. I am not going into that detail right now. You already know. And stack goes in reverse order. So you need to take care of that. Fine? Yes. Okay. Now there is one catch. Again, small. There are two kinds of jump or call. It is called inter-segment and intra-segment. if you are jumping in a same segment, there can be multiple segments. We have already studied segmentation video. So if you are jumping in a same segment, it is called intra segment. If you are jumping from one segment to another segment, inter segment. Intra segment, same segment, inter segment, different segment. Point is, your segment is decided by offset is given by IP. So if I want to access one segment, I am having one CS IP pair. If I want to access another segment, the CS and IP value will get changed. Understand? Each segment, code segment is defined by CS, right? So if I am jumping from this segment to this segment, here my CS value is different. Here also my CS value is different. Understand? Yes? So in jump part, when this down comes, you are actually changing the value of IP, right? To come over here. Yes? Why you are only changing the value of IP? Because it is intra segment. Same segment you are simply jump. So you just need to change IP. But if you are jumping into different segment, in that case you also need to change the value of CS. Understand? Because your CS will also get changed. Same is the concept applicable over here. When you want to jump over here, instead you only need to push not only IP but you need to store your current code segment value also. Understand? Get the difference? When it is intra segment, only IP will get changed. When it is inter segment, CS as well as IP both will get changed. Yes? This is done. Okay. Now what is forward jump? What is backward jump? If I am jumping like this, it is forward jump. I am going ahead in my program. If this jump is over here and my code starts here, I need to go back. So this is my backward jump, right? There is nothing new. In memory, if you are in your code, if you are going forward, forward jump. In your code, you are going back, backward. Fine? Now, there are unconditional jump also. We have already studied in our flag registers video like lecture that flags are used to do unconditional jumping. You are having carry flag, zero flag. So suppose J and Z. This instruction is used to check zero flag and it will jump accordingly, right? Jump if not zero. Jump if zero. Jump if not carry. Jump if carry. These are the instructions that you can use based on the requirement. Okay? We will take one example and you will understand. What is the difference? First of all, there are some unconditional jump. Example is suppose J, M, P, X, Y, Z. X, Y, Z. What this, like how many times this code will get executed? How many times this code will get executed? J and P is unconditional jump. It will not check any condition. So every time when you are on this instruction, it will jump. When it will jump? X, Y, Z. So every time it will come. This is called infinite loop. Yes? Is there any importance of infinite loop? No use? Then why it is there? When you have studied nothing till date, infinite loops are important. How many days you watch your time? How many times watch is required? Like watch should work for how many days? It should not get stopped. It is nothing but infinite loop. If you want to write down a program of watch, how you can write it down? Take 3 counters, second, minute, hours. Second counter will increment until 60, make it 0, make minute counter 1. Again run both the counters, minute counters get 60, make both 0, make hour counter 1, make hour counters reach to 24, make all the counters 0, starts again. This is your program. Write down in infinite loop so that it will run lifetime till your cell gets over of your watch and your watch will work. This is the application of infinite loop. In your traffic signal, how many times traffic signal light will work? Infinite. It should work infinitely. Understand? Yes. So there are requirements where you need to use infinite loop, but it is not used as much as normal conditional loops are used. Okay, but it is also needed. So it is also needed. I think if you ask your seniors, they are working on IoT projects. In IoT projects, they are infinite loop. It will run infinite times. Why it is infinite time? IoT projects behave like infinite times. It should work lifetime. Whatever you want to do it for lifetime. You need to manage. So it is needed. Understand?
Yes, sir.
Forget about it, right? So unconditional jumps are normally used to make infinite loops, but infinite loops are also important. Clear? Now next, I want to make finite loop. How to make CL equal to 5? So I need a loop which runs 5 times. X, Y, Z is my label. Do some task. Jump not 0 on X, Y, Z. So till I get 0 as my flag, it will jump on X, Y, Z. How can I make this CL minus minus? So decrement CL, DEC CL. Yes? Every time decrementing the value of CL, it will become 5, 4, 3, 2, 1, 0. When it becomes 0, my 0 flag will become 1. The condition gets false. I will go to next line. If condition is true, if it is 0, it will go over here. So I can run a loop 5 times. Understand? Simple? Easy?
Yes, sir.
What it do? It actually check your flag. 0 flag. If 0 flag is set, it will not jump. If 0 flag is not set, it will. This is what it do. Yes? There is a catch. Can I write this CL minus minus line anywhere in my program? Suppose this program gets started. Here I am writing CL minus minus. I am decrementing the counter. So after 5 count, it will become indirectly 0. Will it work?
No,
Why no?
because zero flag will
Well, because when you do CL minus minus, your 0 flag will get changed. It is possible that here somewhere down the line you are using some instruction, arithmetical logical instruction, which will change your 0 flag. If there are some logical instruction, it is possible that here my 0 flag will become suppose 1. Then in that case, this instruction will get 0 flag as 1 after this, and it will come out. It should not come out, but it will come out. Yes? Your flags will get changed after each logical instruction. Keep this in mind. Okay?
Yes.
So this instruction will check your flag exactly after this line. So before this line, if your flags get changed, it will doesn't matter. But after this line, if you get changed, that is what your actual instruction will get. So there are chances that you will not get the exact loop that you want. Understand? So keep in mind that this decrement instruction must be exact before your change that condition gets changed. Otherwise, there are chances that it will get wrong result. It is not always giving wrong result. As I said, there are chances that suppose your first line is CL minus minus. Next 3 lines are move, move, move. Now move instruction doesn't change anything. In that case, still you will get the perfect answer. But your programming is not perfect. As a good programmer, it's a sign that you should use your decrement instruction before your jump instruction. Clear? Yes? Understand the difference? And many times it can lead to wrong results also. Yes? Now, this is the instruction that they have introduced in 8085. So when they have launched 8086 after 3 years, they have refined many instructions. Okay? So they have changed this loop instruction, J and Z instruction, and they have replaced and created a new instruction called loop. What? Loop. Now concentrate. Careful. What it do? Move CX, 0005H. CX is my 16-bit register. It requires 16-bit data. I have copied 16-bit data. XYZ colon my code. Okay, LOOP and this will work 5 times exactly. Okay?
Yes, sir.
Can you tell me what are the changes that I have done from that J and Z? First change, in J and Z I have used CL. Here I have used CX. That was 8-bit register. This is 16-bit register. There I have decremented CL. Here I have not decremented CL. I have directly written down loop. Understand? So what your loop instruction internally do? Internally it will decrement CX register plus it will check J and Z and jump on XYZ. 2 instructions that you have written there is performed by this single instruction internally. So you don't need to do decrement. If you decrement yourself, Cx will get decremented twice instead of one time. Understand? Get the difference? In jump not 0, you are decrementing. Here, microprocessor decrement automatically. Okay? Problem is at that J and Z part, instead of CL, if I want to use AL, if I want to use BL, AH, I can use any resistor. Understand? Here, compulsory you need to use CX, not even CL. CX only. Okay? And automatically is always decremented CX. Understand? Yes? Okay. So which instruction is better? Loop or JNZ? If loop is better, then why they have still kept the JNZ instruction? Why they have not scrapped it? It is still there. Okay. And why loop is better? Why loop is better? No idea. Okay. Now J and Z loop. Okay. The default advantage of loop is your number of instruction is less. Yes? So it will be speedy. How the number of instruction is less? In J and Z you are having 2 instruction, here you are having 1 instruction. Yes? You should laugh on me. By saving 1 instruction, how much time you can save? No time. No. It is in loop. So if my loop runs 1000 times, this instruction will save me 1000 clock cycles. If this loop runs 10,000 times, this will save me 10,000 clock pulses. Understand? Yes. So that's why loop instruction will be speedy. Here every time you need to do 2 instructions, decrement J and Z. Yes? Understand? Yes. So it is better than decrement J and Z. This way. Then why decrement and J and Z is still there? It is not scrapped. Because here there is a constraint. It is not flexible. You have to use CX. In J and Z you are having flexibility. You can use AL, BL, CL, DL, any resistor. Simply take the example of loop within loop. You want 2 loops. Then this will get fail. One loop you will use for CX is used for one loop. What about second loop? It will not work. CX is already busy. So you can't use loop instruction. Understand? Yes? So it will give you flexibility that you can use AL, BL, CL, anything. Understand? So J and Z instruction will give you flexibility. Loop instruction will give you faster performance. So if you know in advance that you are not going to use CX for any other purpose, loop is better. But if you know that your CX will get busy for some purpose, use J and Z. Clear? Yes. So there are reasons for keeping both these things in your syllabus and both like in 8.06. Fine? Done? There is always a trade-off between flexibility and performance. Golden case of Android and Apple. Why Apple is better over Android or Android is better over Apple? There is a case of flexibility, rigidness and performance. Something called hardwired, something is not hardwired. Hardwired is always fast. Yes? Apple is rigid in some cases, but because it is rigid, your performance will be more. Android is flexible, you can do lots of stuff, but because of that dependency comes and it will get slow. Understand? So if you go in any case of your life, there is always a trade-off. You need to choose between these two, performance or rigidity. If you are rigid, you can give better performance. If you are not rigid, you can give more flexibility, but performance can be degraded. So you need to balance both the things. Yes? So officially the session is over. We have covered everything that we need to cover. Now some test, logical test. Move, concentrate. Okay, move. What move? Okay, CL, 05H. Instructions D, E, C. CL, comma J and Z, X, Y, Z. This is my X, Y, Z. How many times this will work? 5 times. Very simple. If I make it 100, H, sorry, not 100, we'll take 8 digit number. Suppose I make it 10H. How many times this will work? 16. 10H, hexadecimal number is 16 in decimal. Total 16 times. What is the maximum number that you can store in 8-bit number? F, all one. Yes? What is this number? 255. In 8-bit data, you can store maximum 256 different numbers, and the maximum number that you can store is 255. 0 to 255, total 256. Yes? Yes? This is the maximum number that you can store. If you write H, this loop will get executed 255 times. Understand? Yes. Question. I want a loop which would run 256 times. How can I do that? I don't want to change anything. I want to use 8-bit registers only. Then, what you can do? Bolo. This is the program, same program. I don't want to change my 8-bit register. I want a loop which should run 256 times. What can I do? Concentrate. First you are decrementing or checking? You are first checking the register or decrementing the register? Decrementing the register. If there is a 0, 0 over here, it will get checked first or it will get decremented first? It will get checked first or decremented first? First it will get decremented. If it is a 0, 0, after decrementing what it will get? 0, 0 minus? What is the answer? Minus 1. Minus 1 is F in 2's complement. Very simple. If you enter 0, 0, if you decrement it by 1, it will be minus 1. What is minus 1? Minus 1 is 1 in 2's complement. 1 is 0, 0, 0, 0, 0, 0, 0, 1. This is my 1. How to find out 2's complement? Go from this line. 1 comes, change all other bit. 1, 1, 1, 1, 1, 1, 1. This is F, this is F. F in 2's complement is nothing but minus 1. Yes? So when I entered 0, 0 over here, when it gets decremented, it becomes F. FF is 0? No. It will jump. FF goes here, comes here. FE, no 0. So now my loop will run 256 times. Yes? Huh? So now if I put 0, 1, it will run 257 times. Yes? No. If I put 0, 1, it will come over here, it will get decremented. 0, 1 is decremented to 0, 0. My 0 flag will get set and be out of the loop. It will run only once. Yes? So using 8-bit of data, you can run a maximum of 256 times a loop. Clear? Why? This is the solution. Complete? Yes. Done. This is it.